Straß. Weierstraß.
No. We will talk about.
What was the title? The inverse problem, I think. In any case. Okay, for those who do not know me, because I see quite a few known faces. For those who do not know me, my name is Michiel, and I come from I would say my background is something of a small research school, which was originally centered in Eindhoven and Bath, where we try to prove connections between large deviations of particle systems on one hand and gradient flows on another hand. Okay. And I'm happy to say that by now we understand much more than we did, say, 6-7 years ago. But there are still a couple of loose ends, and today I want to talk about one of those loose ends. This is really still a loose end, but I thought it would be interesting nevertheless. And it's joint work with Johannes Ziemer, who couldn't make it today, but he should be here tomorrow. Okay. So, large deviations and gradient flows. Let me first start with the question, why? Why should there be a connection between large deviations and gradient flows? Why connection Is this readable in the back? Yeah. Okay, super. So I know that I'm being extremely vague here, and lots of you probably don't have the slightest clue what I'm talking about, but I will get there in due course. So why should we have such a connection between large deviations and gradient flow? Well, I would say for two reasons. It's just two reasons that I want to talk about today. One of those reasons is that gradient flows are often driven by an entropy functional, and an entropy functional itself is closely related to large deviations. Let me explain that. If you already know this, then you can sleep now and I will wake you up later on, okay? So entropy closely related to large deviations. Okay. So imagine you have a number of random variables that are independent. In some state space, and they all have the same distribution, say mu. Probability mu, which is some fixed probability measure. Okay. Now I'm going to look at the empirical measure, which is also what Patrick already talked about. I'm very grateful for that. I'll give this thing a name. Which is this thing. This is itself a probability measure, of course. But it's a random probability measure. So random variable in this. And this is a random probability measure that counts the number of particles that are in a certain set. And of course, if the probability mu is high in a certain set, then you would expect to see more particles there. So it would make sense that you could have something like a law of large numbers, which you do indeed. And this says that this thing will converge to mu. Now I want to stress here that This is a random variable. This is a deterministic. It's a probability measure, but it's a deterministic probability measure. Yeah? Yeah, oh, I wrote it a bit too small, I guess. Yeah. Okay. So for large n, this thing is going to be close to this. So we can also ask the question, what is the probability that it's not close? Probability that, and I'm going to use some fake notation, which is more or less accepted, I would say, in the community. It turns out that this probability converges to 0 exponentially in n with some rate which is an entropy functional. Okay. What I write here, if you don't know what this means, then just think of this as an exponential rate of convergence. If you do know what it means, well, then you know what it means. But this is short notation for a large deviation principle, and this theorem is called Sanoff's large deviation principle. Exactly. It's just a dummy variable. Yeah. Okay. So that shows that entropy is indeed closely related to large deviations. Okay. Yeah. Another reason why there might be a connection between large deviations and gradient flows is that they both have very natural variational formulations. This also gives handles to see if there's a relation, of course. Well, but a gradient flow is something, it's an evolution equation in time. So before we can make a connection, we need to introduce a time parameter. So let's see if we can do something along these lines, but now with a time parameter. So let's say we have some sequence of random variables. And these are Markov processes. That converge to a deterministic evolution. Such that or maybe we want the entire path to converge. Now we use this notation. This is now a path or a trajectory. Like this. Now this is again a deterministic limit, but it's an evolution. Okay? So think about, it probably satisfies some limit equation. Sorry? So what you can think about here is For example, I never understand why it's not FE but EG. It's Latin, is it? Yeah, okay. EG, you could take the time-dependent empirical measure, and here, for example, independent particles. You could do that, and then you could see this as some kind of law of large numbers on path space. Okay. Yeah, but I really want to be a bit more general here to allow a bit more abstractness. Okay. Right. So this thing on the right is now again a deterministic limit. But it probably satisfies some equation. So limit equation, say it looks something like we have some operator, something like this. Okay? Okay. For Markov processes, I won't say that it's extremely simple to prove a large deviation principle. Richard will talk about that. I think he will talk about exactly this case. Exactly, but at least if there is a large deviation principle, then it is always of the same form. So I'm going to look at the probability of a certain path. This is now a dummy variable again. Like this. And whatever this L is, of course it depends on the process that you're looking at. Right? But I want to keep this a bit abstract here. There are a few things that we know about this L. We know that it should be positive, because if this is positive, then this thing converges to 0, which is exactly what we want, except for one case, and that is if we are in the deterministic limit. And then it should converge to 1, which means that this should be 0. Right? So we have this thing is always non-negative. And it's only 0 if it satisfies that equation. Is that clear? Okay. So that's for the large deviation part. It comes with natural variation of formulation. Okay. So how about the gradient flows? Well, there are in fact many variation of formulations of gradient flows, but I'm only going to discuss one thing. So this is large deviations. And I'm going to write linear, because I also want to come to a nonlinear, and this will be clear later on what I mean by this. I'm looking at an extremely oversimplified category of large deviations, namely those on a manifold. Okay, so what is a gradient flow then on a manifold? Oh, it's an equation it looks like this. We have some entropy functional which should be differentiable. Then this derivative is something that lies in the cotangent space. This derivative, of course, lies in the tangent space. So we see that this operator should map cotangents to tangents. In order for this to be a meaningful gradient flow, which means that we want the entropy to decay in time, we are going to require that this is symmetric and positive definite. And we're going to need this later on. Okay, but this is a condition that that guarantees that the entropy will decay over time. This is an operator. So this operator is acting on that has to be symmetric. Look, okay. I have a dual pairing between cotangent and tangents. I can make that into a Hilbert space using this operator. So I can define something like gamma 1, and now this operator, mu, gamma 2, because now this lies in the tangent space, and this lies in the cotangent space, and that thing should be symmetric. Yeah, good question. And in the same way, you can define positive definite. Okay. So indeed, this was already a bit where I want to go to, because this K defines an inner product space. And the thing that we will be needing most is the norms that it defines. Norms on T star. That's clear. That's exactly this construction here. Sorry? Psi are cotangents. Yeah? Okay. And it also defines a norm on the tangent space via Legendre transform. I'm going to write this with a half here. Okay. So I have norms on the tangent space and a cotangent space. Now I can write down the variational formulation, which looks like this. A half right. So because these two norms are Legendre duals of each other, this expression is always non-negative. It's just Legendre Young differential inequality. Okay, so this thing is always non-negative, and in fact it is 0 if and only if we are in this situation. Hey, this looks familiar. Okay, I don't want to go really deep into the nonlinear case, but I will need it somehow. So let me just briefly mention that we can also do something like nonlinear, or some people call it doubly nonlinear. And then we're going to replace these norms by general potentials that are Legendre duals of each other. And then the same thing looks like this and equal if and only if punch you have it. Sorry? Well, that's kind of an extreme case, but you could think about that. Exactly. So maybe it's good if I continue a bit and then I give some examples. Okay. Yeah. Yeah. Okay. So. Of course, I have been a bit suggestive in my talk so far, because I've only mentioned two variational formulations that are somehow close to each other because I want to connect these two. There are many different possibilities to connect large deviations to gradient flows, and I'm only going to discuss this one. Right? Because this is something that I'm going to use. But there are many different ways to do it. Okay. So let's call this. Hey. Let's go to part B. Where I don't want to spend too much time on it, but I call this the forward problem. So think about this. You have some particle system in mind, and you are able to calculate the large deviations like this. Okay. So then you know what your L is. And now I want to know, are these large deviations somehow connected to a gradient flow? So of course, I can make a beautiful connection if I can show that this L is exactly of this form. Then I'm done. Right? Because then I have a variational formulation which is the same. So the question is, if I know what my L is, can I find, so this is more general than this, so can I find psi star and an entropy functional such that this L is exactly the same as this? Okay? So this turns out to be not at all that hard. This is a theorem that we proved with Alex Milke, Mark Pelletier, And me, I think it was published about 1 year ago or something. So we're given an L. There exists, let me see, unique such that L can be written like this. It turns out that this is always possible, but that does not necessarily make it a meaningful gradient flow, because again, we want to require that the entropy always decreases. So there should be additional conditions, which was in the linear case, this one. And in a more general case, it's the fact that these potentials should both be 0 in 0. Okay? It basically means that if your system doesn't change, then you don't want to dissipate anything. So there exists unique such that this holds if and only if and only if the derivative of this L in 0 should be the derivative of the entropy function that you were looking for. As soon as you have this, then you're done. It's not that difficult to see, in fact. Okay. Okay, 2 examples. Yeah, sure. It has to satisfy this, and it has to be convex.
And not necessarily the wave function.
No. Yeah, good question. So, yes, something that I didn't mention here. This condition is always satisfied if it is a large deviation rate functional and your system satisfies d-dot balance. So this was my Markov process, for which this L was my large deviation rate. Balance. No. That would be very interesting. I've been thinking about that for a long time. Yeah. But okay, yeah, that's a bit cryptic, is it? Yeah. So let's say that this S is yeah, I can do it like this. Maybe I should just write it like this. So as soon as you have your L, then by this determines what your S should be, well, up to constants, okay? But you have no other choice than that. So in that sense, it's unique. Okay? Thanks. Okay. Example number 1. I'm again looking at these. And these are independent Brownian motions. So the large deviation for this thing is a odd result, and if I apply this, I will get that my S rho log rho, where this is with respect to Lebesgue densities, and my psi rho S is this one. So in this case, I do get that my psi is of this form. So it's in fact a linear gradient flow in this sense. And in fact, this is the Wasserstein gradient flow. Wasserstein gradient flow. Okay. Example number 2. I take the same thing, but now these are independent Markov chains. So that's on a finite state space. And let's say they all have the same generator. Matrix Q. Okay. Then it turns out, okay, let me assume that this Q satisfies Little's balance. Then it turns out that I really, really need this nonlinear structure. So then S rho is going to be and this is the invariant measure. And my psi, let me write down the psi star because that's a bit easier. That's it. It just happens to be of that form. So we can say that it does yield a gradient flow, but there's not a linear one. This is a very interesting thing because this is different than the structure that was found by Jan Maas and Alex Mielke, the discrete structure. And that structure has the same entropy function, but a different dissipation potential, because that one is quadratic. It's just a linear gradient flow. That poses interesting questions. Let me write that. So different so the entropy is the same, but this is now a linear thing, which is of this form. In this case, just a matrix, because we are in a finite dimensional space. And K is, what was it again? So this is a matrix. I think it's this one. Yeah. So from large deviations, we get something different. We get a nonlinear structure. But immediately that raises the question. So these are both gradient structures for the same equation. The equation is just a system of ODEs, where Q is the matrix. Yeah. They're both gradient structures for the same equation, both with the same entropy. Only the dissipations are different. So if this one is related to a large deviation principle, how about this one? And lots of people have been thinking about that, and we've been trying to construct it using Brownian motions and all kind of things, but it never really did work. We always ended up with something quadratic again. Very frustrating. In the end, we realized that we should do something completely else, completely different. And this is, so I'm now going to the third part, which is what I would call the inverse problem. It's maybe interesting to say that in a early overview paper by Adams, Deer, Pelletier, and Ziemer, I think it was 2012 actually, or published 2013 and first on ArcSci. And they write a conjecture. Each gradient flow structure can be connected to an appropriate stochastic process via a large deviation principle. It's kind of a bold statement, but why not? Why not? So this is the question that I now would like to think about. So, I just wiped that out, okay. So comparing with what we just had, where we were given an L, and we're thinking about whether it's related to some gradient flow. In the other way, this is trivial, because if we know what the psi and the psi star and everything is, we know what the L is. But the question is this L a large deviation rate function for some stochastic system? This is really the question. So the problem is, given L, that we're simply going to define to be this form. There we have our L. Wasn't that hard. So the question is this a nice deviation? Right. So can we find some stochastic process such that okay, how many of you are familiar with large deviations techniques? Quite a bit, okay. Okay, great. Let me see if I can squeeze that in the time. So here's our first, okay, it's not our first approach, but it was our first approach that actually led to something. Let me rephrase that. So we want this thing to satisfy a certain equation. So this would be the deterministic equation, and I'm simply going to perturb it by some noise, and then think about what this noise should be. And I want this noise to vanish in the limit, because in the limit I want to find this deterministic limit and do gradient flows around that limit. And turns out that the right scaling is square root of n. And we have some noise. So what should this noise be? What kind of noise should we choose here? So we tried all kinds of things, but in the end we realized that oh yeah, so this is in case this wasn't clear, this is with Johannes Zimmer. In the end, we realized that this noise should lie in the same space as this thing, which is the tangent space. Okay. Now, on the tangent space, because we're on a manifold, on this tangent space, we actually have a Hilbert space. And on a Hilbert space, you can always define something like white noise. Even in a very, very abstract setting, you can always define this. And this is called the Bochner-Minloss theorem. We're going to look at the Fourier transform of this thing. But at least formally, once we have this, then we also have a Laplace transform. You just plug in the same psi with the I in front of it. Yeah? And let me put this rescaling in there as well. So this is this thing. Then we also have I to the yes, n. Hmm? Over the path, over the entire path. Nope. Yeah. So think of this thing as an expectation over path.
Yeah, of course. Oh, it's over the W. Yeah, yeah.
Yep. Okay. Okay. Then we just get this. And sorry? This one. So I got rid of that, and because of that I got rid of the minus here. So this is of course you have to do some work to show that you can actually do this, but if you can do this, then you have a Laplace transform. Yeah. Okay. And this is actually exactly what you need to calculate in order to prove a large deviation principle. Once you have this, then you can use Gardner-Ellis. So Gardner-Ellis. That tells you that this one. And now we're almost there, because we can simply plug in this equation, this one. If we know what the fluctuations of this thing are, then we know what the fluctuations of this thing are. At least if the equation has a strong solution. Yeah? So let's say for any realization of the noise, the path of rho is completely determined. And this has to be a continuous mapping, blah, blah, blah. It's hard work to actually show this. But if you can do this, then immediately from this, we get you can see this, by the way, as an abstract Schilder's theorem. A half, and then we get rho t plus kt. Oh, I forgot to invert here. This one. And that was exactly what we were after. Because if you expand the squares, you see that it's exactly of this form, at least for quadratic functionals. So this is exactly what we were after. So, well, you would say problem solved. On to the next one. But there's something fishy going on here. Does anyone notice this? Okay, there's lots of things fishy going on here, but one thing in particular. The norm that I've used here, depends on my state rho, which is particularly fishy because I want to define rho in terms of the noise, but now my noise depends on rho. That is particularly fishy, I would say. We really don't want to have that. Yes. You're right. But this doesn't work. I mean, it works, but it's hard to make this rigorous, right? Because now rho is coupled to W and W is coupled to rho. But but we can even do better than that. There's an easy way to fix this. Easy. There's a way to fix this, which is the following. That's it. Yeah. So I want you to think about this operator k that we had. So this mapped cotangent space to the tangent space. And we use this k to define the noise, okay, this operator. Now if we could find some space in between here that is independent of the state, then I claim that we are done. So again, we need some Hilbert space in order to define noise. And I want to have an operator here and an operator here. But I want this thing to be the adjoint of that. In other words, I want k of rho to be or is it the other way around? It's the other way around. Okay. For now, this looks like it falls out of thin air, but it's not that strange if you think about the fact that on a manifold, every tangent space should be isomorph to a invariant space, or typically if you're looking at Markov processes, you have if it's reversible, you have an invariant measure. So some canonical tangent space would also be the tangent space at that canonical measure, and then you need some parallel transport to map your tangent space to this one and map it back. So it's not that weird to think about. Yep. Yep. Exactly. Good point. I will come to that quickly. So now, this is my fix, because this is not good. This is not good. So the fix is, I'm going to look at this equation. I'm going to define noise in this space and then map it to the tangent space with this operator. Now the noise is independent of the state, okay, and and this thing lies again in the tangent space. So this is all well defined. Right. So I won't do the calculation because it's basically the same as this, but now it works. Okay. And yeah, once you see this, you might realize that it's not at all that shocking, but still it took us quite a while to realize that this is the right thing. Two examples. This one.
Yeah, so you say there's a space H between two values, which is row independent.
Okay. Let me rephrase that. If you have such an H, then you can do this.
Yeah. Okay. Yes.
Okay.
Yes. Perfectly.
But I'm giving some examples in which I want to show you that this is not completely ridiculous.
That's a win-win situation. Fine.
Yeah. But okay, thanks for clearing that up. How much time do I have? Okay, I will manage. Yeah. Do you like cold coffee? Example 1. What happens if I took my example from the start, where I had independent Brownian particles? Then I could calculate the large deviations and get a gradient flow from that. What if I work my way backwards and see what my stochastic system gives? Okay. So we had this thing. Maybe write it like this. This one. And so this one is now H1. My K operator is the Wasserstein operator. This should probably look familiar to most of you. Okay. Rho. Now I'm going to take a row, so a or a d row. Square root of rho times the gradient of psi, and the transpose of that thing is now W. Sorry? Sorry, you're right. This is L2 from, let's say, RD to RD. Sorry, you're right. Yeah. But it should be clear that these two are adjoints of each other. And it should be clear that if you combine them, you get this one. There you go. So you get the equation where this white noise is now defined in this space. Okay, it's a very nasty object, but it's well known. Well, it's known. That's put it in that way. Johannes calls this the Dean equation. Some people would call this the super Brownian motion. Motion. And in fact, this describes exactly the particle system that we started with. It's just another way of writing it. Okay. So, example 1 and last example. Which is not at all that shocking, I guess, but still interesting. What if we start with this, with this one? That's what motivated the question in the first place. Well, as Patrick already noted, if you have a matrix that is symmetric and positive definite, you can always define square root. The space is just RD to the RD, so there's no problem there. So we just get, yeah. So this is the deterministic one plus 1 over n square root of my K matrix. And this is now just ordinary standard how many did we have? I-dimensional white noise. So this structure, this construction, once you can do this, you can always find a stochastic system that is related to a linear gradient flow. This is all linear gradient flow. We can't do nonlinear gradient flows. The problem with these nonlinear structures like this one, it turns out that you can never use additive noise or multiplicative noise or whatever you want. It's much more involved than that. So this is all bound to fail if you're going to do additive noise. Yeah. Pancho looks very puzzled. Well, here I have. Well, let me write that. Look at the right one. This one. This is the limit that I want to look at. I simply add the noise here. That's not going to work because you see we use this contraction principle, and then we found that our large deviations are of the form this minus this. But our large deviations are not of this form for a nonlinear structure usually. So this whole construction is not going to work. Okay. So this is still work in progress and very formal, but I hope to at least tell you something interesting. Thank you for your attention.
Thanks, Michiel. We're already over time, but in time for one question.
Pancho already posed the question.
So if there are no questions, then talk is outside there. Thank you, Michiel.
Yeah.